Nobody would want to enter a dangerous environment, such as a steel mill, without the proper protective gear. Flame-proof clothing, hard hats, and steel-toed boots are essential on-the-job tools here. But many people insist on working around optical fibers without any sort of protection. Although the obvious dangers of the steel mill are not present with fibers, the opportunity for injury still exists. Optical fibers, most of which are glass, pose hazards for the unwary. Fiber fragments or splinters can easily penetrate fingers, toes, or eyes and can be difficult to remove. A pair of Teflon-coated tweezers will make the removal of fiber fragments a bit easier. The most obvious form of protection to prevent such occurrences is protective eyewear. The clear plastic lenses can stop a fiber end from piercing the eyeball or prevent minute fragments from entering the eyes. Flying glass fragments are often the result of cutting and cleaving operations. What is worse is that the presence of these fragments often goes unnoticed due to their small size. When working with an optical fiber, choose your work surface carefully. A chemical-resistant, non-reflective surface is ideal for laboratories, while a black mat serves well as a temporary work surface. A dark working surface provides contrast against the clear fiber. This allows for safe handling and disposal. Because fragments can stick to skin oils, thoroughly wash your hands before touching your face or eyes after working with fibers. Safety glasses cannot protect you when you defeat the purpose for which they were designed. Your best weapon against injury by fibers is common sense. Eating and drinking around fibers is dangerous. Bits of fiber can fall into drinks or stick to food. In work areas, smooth floors like tile or concrete are preferable because they can be swept clean after optical work is performed. In carpeted areas, it can be very difficult to find and safely remove fiber debris. Computer rooms with raised floors covering cable runs can pose hazards to unsuspecting technicians. Because the rooms are usually pressurized with the underfloor areas acting as air ducts, a sudden gush of air can result when a tile is removed for cable access. Fiber chips may be blown into the eyes of those not wearing safety glasses. For this reason, it is imperative that safety glasses be worn and that fiber debris not be dropped into open floor tiles. The installer not only has the responsibility for his or her own safety, but for the safety of others who may come in contact with the fibers or their waste. Many installers place waste fiber ends on a length of adhesive tape. When the tape is full, it's folded over and discarded. This method is not very efficient, and those who use it will soon get the point. A better way of dealing with waste fiber ends is to use a small plastic bottle with a screw-on cap. Sharp fibers are safely contained until proper disposal is available. Pop-top bottles should not be used for this purpose, because a fumbled opening could dump the contents. Fiber waste must never be put in ordinary garbage for routine disposal. To make more room in a wastebasket, someone may try to compress the garbage, only to receive a nasty surprise. It is best that garbage containing fiber waste be sealed and disposed of by the fiber craftsperson. One of the major advantages of fiber systems is the ability to transmit over long distances using the solid-state laser diode. It is obvious that the high-power diode lasers used with low-loss optical fibers can be a potential eye hazard at points distant to the laser itself. The lasers used as fiber sources operate at 850, 1300, and 1550 nanometer wavelengths, which are all in the infrared part of the spectrum. These first two wavelengths, along with the visible wavelengths of light, are focused by the eye onto the retina. Retinal receptors are sensitive to the range of wavelengths between 400 and 700 nanometers, but not to wavelengths outside that range. Herein lies the danger. Although a person cannot perceive the intense light from the laser, it is still being focused on the sensitive retinal tissue. At the focal point, energy density can be high enough to burn the tissue, resulting in loss of visual acuity or in blind spots in the person's visual field. This is true even though lasers for fiber use are actually of low power compared to other laser types. There are literally hundreds of laser types that are used in a multitude of applications, ranging from communications to welding. The lasers with the highest power outputs use gas molecules or crystals doped with various lasing materials to produce their laser beams. Lasers for use with optical fiber are made from semiconductor materials that feature low voltage, high-speed operation. Because of safety concerns, there are government regulations regarding the use of lasers. Lasers are classified into 4 general categories according to their accessible radiation during normal use and maintenance. The class of an individual laser depends on its operating wavelength, its output power, and whether it is pulsed or continuous wave. For our discussion, we will concentrate on the infrared lasers as they are addressed in the ANSI Z136.2 standard, but we will briefly cover some higher power lasers as well. Class 1 lasers are considered eye-safe, in that no damage would result even from prolonged exposure to the direct beam. Because shorter wavelength light, especially wavelengths shorter than 550 nanometers, is more heavily absorbed by the retina. The maximum output power of Class 1 lasers generally increase with increasing wavelength. As laser emission at wavelengths greater than 1400 nanometers is absorbed by the cornea, no focusing onto the retina occurs, and the Class 1 laser maximum output power increases dramatically. A person's natural aversion response to bright light will cause the eye to blink and the head to turn away. Class 2 lasers are those for which this aversion response will protect one from the output. Thus, Class 2 lasers include only those emitting visible radiation, while helium-neon lasers used in many fiber identifiers fall into this category. No Class 2 lasers are used in telecommunication systems. Class 3 lasers can be ultraviolet, visible, or infrared lasers with outputs greater than Class 1 or 2 devices, but less than 500 milliwatts. Many helium-neon lasers and visible diode lasers are Class 3. Even brief eye exposure to Class 3 laser radiation can be dangerous. Class 4 lasers have the widest range of output powers from 500 milliwatts to the megawatt level. Output powers of several watts can easily burn paper or flesh, while power levels between 200 and 1500 watts are used for materials processing. Carbon dioxide gas lasers like this one operate deep in the infrared part of the spectrum at 10,600 nanometers, making them unsuitable for use with glass or plastic fibers. In fact, CO2 lasers readily cut glass. At the high power levels, even reflected beam energy can start fires or cause severe burns, so regulations dictate that special beam containment equipment be used with such lasers. The long wavelength of the CO2 laser is absorbed by the cornea of the eye, so it never reaches the retina. This, however, does not make it an eye-safe laser. When eye components absorb beam energy, their temperature can instantly rise to the vaporization point, causing appalling injuries. While the ANSI standards call for safe use of lasers in fiber systems, it is important that the characteristics of all laser sources be determined to assure compliance with the standards. All lasers used with fiber communication systems are well below the energy levels that would cause skin burns, but the danger to eyesight is very real. The danger is highest at optical output ports where energy is coming directly from the laser. This is particularly true of active housings that contain laser chips in the connector ports. Never look directly into any optical port. Unused ports should be capped to prevent accidental exposure, and equipment should never be mounted at eye level. The numerical aperture of an optical fiber indicates the extent to which laser light spreads upon exiting the fiber. The larger the numerical aperture, the greater the spread angle. The more spread out the laser light is, the less of it can enter your eye and be focused onto the sensitive retina. Fiber attenuation also lowers the laser power, so the farther away from the source, the lower and safer the power level is. Keep in mind that the 850 and 1300 nanometer wavelengths are focused onto the retina, whereas the 1550 nanometer wavelength is not. Therefore, fiber optic systems operating at 850 and 1300 nanometers pose much more of a hazard than those operating at 1550 nanometers. As video transmission over fiber increases, the trend toward higher signal-to-noise ratios will require the use of laser emitters in excess of 1 milliwatt or Class 3 operation. In addition, if the laser is packaged as an active device, the beam would be highly directional, causing even greater safety concerns. Equipment that contain lasers is required to have proper labels at the ports where optical energy is emitted. The label must state the type of laser, its class as well as precautions, and a brief warning message as to the type of danger the laser presents. Since patch panel manufacturers do not know what types of light sources will be cross-connected at the panel locations, many provide safety labels already on their products. Since the actual laser type may be unknown to the supplier, these labels may not supply the proper information for adequate safety guidelines. Safety labels may be purchased through many suppliers to meet actual performance specifications. Those who work with lasers that could exceed safe exposure limits, as outlined in the ANSI standard, should wear protective lenses that are designed to highly attenuate laser energy at key wavelengths. Laser safety glasses are available for every type of laser in use today. In addition, broad-spectrum glasses are available that could be used with a number of laser wavelengths. However, glasses that are designed for a specific wavelength usually offer better protection than the broad-spectrum models. Prior to using an inspection scope to visually inspect a connector, use a power meter to confirm that the fiber is not transmitting optical energy. Fiber technicians may encounter another optical hazard, completely unrelated to lasers. The UV curing lamps used with some types of splices or connectors can be dangerous. They produce both long-wave ultraviolet light with wavelengths between 320 and 400 nanometers, as well as shortwave UV with wavelengths shorter than 320 nanometers. The shorter the wavelength, the more dangerous the radiation. Shortwave UV can induce chemical changes in living tissue that can cause malignant melanoma for skin exposure and can damage the cornea. Many UV curing lamps have internal filters to eliminate the shorter wavelength energy, and exposure to the longer wave UV is safe, providing the person does not stare into the light for prolonged periods. When using these devices, even ones containing filters, it is a good idea to never look at the light, because UV damage to eyes and skin is cumulative. It is a fact of life when working with fibers that the technician will come in contact with a variety of chemicals. Solvents like isopropyl alcohol, as well as the adhesives used in fiber connectorizing, are among those encountered. When working with solvents, there is always the possibility of fire. Solvent vapor can build up in poorly ventilated areas where a cigarette or the discharge from a fusion splicer could cause an explosion. Smoking is never recommended when working with fiber anyway, due to contamination problems. Due to the small size of optical fibers, contaminants like smoke particles can ruin or degrade a perfectly good connection or splice. Solvent bottles should not be left uncapped, as they're easily knocked over. In addition, solvents exposed to the open air will quickly absorb atmospheric moisture, as well as other contaminants, making them less effective as cleaning agents. A better way is to use disposable solutions, such as Elco pads and optic pads for all fiber cleaning applications. They are inexpensive and easy to use and will reduce the risk of a solvent fire. There are many types of adhesives available for use with fiber. Many of these are epoxy-based and require mixing prior to use. Epoxy adhesives can be strong skin and eye irritants. When using chemicals or epoxies, a well-ventilated area is recommended and may be required depending on the chemicals used. UV curing adhesive has a low viscosity and is often supplied in syringes. If the tip clogs and more pressure is applied, the adhesive may suddenly squirt from the syringe, possibly entering the eye of a bystander or the fiber technician. This type of accident can be prevented by the use of safety glasses. Other chemicals commonly encountered are index matching fluids, cable pulling lubricants, and cable moisture repellents. Any of these chemicals could cause irritation or possible allergic reactions in certain people. Proper clothing, including gloves and eyewear, may be required for a safe workplace. In addition, it is recommended that good cleaning habits be developed after working with chemicals, especially prior to eating. Government regulations require all chemical manufacturers to provide material safety data sheets with any chemical product sold. This includes benign chemicals like alcohols to highly toxic poisons like cyanide. The MSDS cover the identity of the substance, the hazardous ingredients, any physical hazards, health hazards, and information regarding protective clothing required while using the substance. In addition, the MSDS will contain special precautions for storage of the substance and steps to be taken in case of spills. MSDS legislation are known as right-to-know laws. Employers must make these data sheets available to all those who will work with the chemical product, but it's up to the individual technician to read the data sheets for his or her own protection. When installing fiber cable, there are a number of safety concerns to be aware of. Manholes and underground cable vaults can collect poison hydrogen sulfide gas from nearby sewer systems or other heavier-than-air poison or flammable gases. Gases can overcome and kill a person within seconds, so this hazard is not to be taken lightly. A gas analyzer should be used to ensure gas is not present before entering the manhole. In addition, ventilation equipment should be used when working underground, and in some cases such equipment is required. When pulling cable with power-driven winches, care must be taken so that clothing does not become entangled in the machinery. Never stand in line of pulling lines, cables, or hardware under tension. If a sudden break occurs, the whiplash effect could cause serious injury or even be fatal. Lubricants are sometimes used to decrease the tension caused by friction during cable installation. Lubricants have low viscosity and are extremely slippery. In case of spills, an absorbent material like sand or sawdust can be used to temporarily prevent accidents until the spill can be properly cleaned up. Aerial installations come with their own set of dangers. Many fiber cables are installed on existing power utility right-of-ways. Although the proximity of high voltages does not affect the fibers, it does pose hazards for human installers. High voltages will arc across airspaces to an alternate path to ground, such as ladders, lift equipment, and human flesh. If you become an alternate path to ground by touching or coming too close to a power line, you will be severely burned or even killed. Occupational health and safety codes provide for absolute limits of approach to aerial power lines. These distances depend on the level of voltage in the lines and range from 3 to 5 meters. Even when an aerial cable is installed between poles not carrying high voltage lines, shock danger may still exist. Long lengths of cable may build up lethal amounts of static electricity that will discharge through a person attempting to work on it. To prevent this, grounding clamps should connect the cable exterior with a good solid ground at each pole site. Metallic messengers must also be grounded in this manner. This will also better protect the cable from possible lightning damage. In addition to electric shock hazards, those working on aerial installations must be careful to avoid falls or dropping heavy articles on people standing below. Hard hats, heavy protective clothing, and thick gloves are a must in these situations. While working at night, proper reflective colors must be worn and the appropriate signage used to meet or exceed the local, regional, or federal safety requirements. It cannot be stressed enough that the proper safety equipment be worn at all times while working with fibers or fiber cables. From simple eye protection from fiber particles to full body protection while installing cable, your safety equipment used along with good common sense will protect you from disabling or even fatal accidents. The small amount of time it takes to put on the safety gear is well worth the effort. If you won't do it for yourself, consider doing it for those who care and depend on you.